All right, starting Unit 2, which will comprise of Chapters 3 and 4. Chapter 3 is called Stoichiometry, which we'll get a definition for in a second. And today's lecture is going to cover 3.1 and 3.2 in the text, counting by weighing and atomic masses. Chemical stoichiometry, the study of quantities of materials consumed and produced in chemical reactions. Let's take a look at a general reaction. Here we've got methane. And we're going to burn it, so we're going to add some oxygen to it, which we do anytime we burn it. It's a little delta sign. The delta sign on top of the arrow actually means heat is being added. And the two things that will get out the backside are carbon dioxide and water. Now let's say that we started with 5 grams of methane, and we started with 4 grams of oxygen, and we were going to ask how many grams of carbon dioxide were produced. Now when we're trying to figure out the amount of product produced, we can't simply look at the masses of the reactants. Chemicals don't react based upon their masses. They react based upon the amounts of molecules and the types of molecules involved. Well, we don't have a scale small enough, at least in our lab, to weigh individual molecules and atoms. Instead, we weigh large samples of methane and large samples of oxygen. So it's going to be important to know, well, in those large samples, exactly how many molecules are there. Well, I'm not going to count these because that would take us forever. So we have to use an interesting method. We have to use the method known as counting by weighing. It's pretty simple, actually. Let's say you've got, I don't know, a bag of peanuts. I'm going to try to draw a peanut here. That's a peanut. All right, say you've got a bag of peanuts. It's a huge bag, and the bag itself weighs 50 pounds. Let's go metric, 50 kilograms. And one peanut, you find out, has a mass equal to, let's say, 2 grams. And somebody came along and asked you, well, how many peanuts are in that bag? Well, you could do 2 things. Number 1, you could count each one of them. Or number 2, you could use a method of counting by weighing. Knowing that each peanut weighs 2 grams and the bag itself weighs 50 kilos, you could see, well, how many peanuts is it going to take to make up 50 kilos? Should be a pretty simple calc. 50,000 divided by 2. And in that bag, you've got 25,000 peanuts. A lot of peanuts. Now you might be saying, well, wait a minute, Mr. Cornick, not every peanut is the same size. Ah, very, very good question. I hope you're saying that at least. So let's talk about that for a second. My question to you would be, yeah, you're right. Or that'd be my statement. Yeah, you're right. Not all peanuts are the same size. And then my question would be, so let's take this into the chemistry realm. Are all elements the same size? You know, like if I have 16 carbon atoms, are every single one of them the same exact size? Hopefully your answer would be no. You'd say, no. I remember learning about these things called isotopes. Let's take a look at carbon, for instance. Carbon has an atomic mass of 12 in some instances. In some instances, it's 13. And in very rare instances, it's actually 14. So we want to actually know, well, how do we know, like our bag of peanuts, for instance, how do we know what the average mass of the peanut is? That's a viable question to ask. We also kind of want to know, well, what are these masses and how do we find them? Well, this is the instrument that we use. It's called the mass spectrometer. And the idea here is that we send a carbon sample into the mass spectrometer and it gets exploded, it gets blown up. And the most massive ions, so the carbon 14s, end up on the bottom of the plate by my orange line. And the least massive ions, so the carbon 12, end up by the top of the plate, okay, by the red line. And what we find from that is a ratio. And in fact, we find a specific ratio for carbon. Let me show you that ratio now. For carbon, the mass, and this is in your book, of C13 compared to the mass of C12 actually equals 1.0836. Okay. Well, by definition, and your book states this, carbon-12 has an atomic mass of 12, exactly. So if you were to ask, well, what's the mass of carbon-13? Well, that's just 12 times 1.0836. And you'd find out that the atomic mass of carbon-13 is 13.003, with a lot of other decimals down there. And that unit is the atomic mass unit, the AMU. All right? So where are we going to use that? Well, we're going to use that in actually finding the average atomic mass of carbon. And that's the number you should be familiar with from the periodic table. So here's the math that we do. We said carbon-12 has a percentage abundance of 98.89%. And we said that carbon-13, or more precisely, carbon-13.0034, has an abundance of 1.11%. Now you may be saying, wait a minute, Mr. Cornick, what about carbon-14? Well, if you go back to the other slide, you're going to notice it's like negligible. There's nothing there. So because of sig figs, it actually wouldn't play a role in our average atomic mass. If you know how to do the math with percentages, this shouldn't be too difficult. There's the setup. And your final answer is 12.0 AMU. And it's that number that should be, again, familiar to you. Okay? That's the number on the periodic table. So we've got a couple of names for that. The average atomic mass. And historically, it was also called the atomic weight. So you may hear those both interchangeably. AMU is kind of goofy. You know, gram's easy. We know what a gram is. It's about a paperclip. Okay. Well, what the heck's an AMU? Well, it's defined as this. You ready? 1/12 the mass of a carbon-12 atom. So essentially, it's the size of a proton. So 1 AMU equals 1 proton. Just keep that in the back of your mind. All right. Now, I might ask this question sometime. I might say, if you had a bowl full of carbon atoms, what would be the chances of you picking out a single carbon atom that had a mass of 12.01? Now, hopefully you'd be smart enough and say, well, your chances would be 0. And you'd be correct. Now, 12.01 is not the mass of a single carbon atom. Just like we probably, if we had that average mass of all the peanuts in the bag, we probably wouldn't pick out a peanut with exactly that mass. Instead, 12.01 is an average. And for stoichiometric purposes, when we're trying to calculate out how much product is being produced in a particular reaction, it's that number, the average atomic mass, that's going to be important to us. And it's this number that allows us to count atoms of natural carbon by weighing. It's this number that allows us to essentially calculate the amount of peanuts in the bag without having to count them. Let's try an exercise. You got an element that consists of 62.60% of an isotope with a mass of 186.956 AMUs and 37.40% of an isotope with a mass of 184.953 AMUs. I want you to go ahead and calculate the average atomic mass and then identify the element. So pause the video, see what you get. Alright, so if you did your math right, you should get 186.2 AMUs. And if you search on the periodic table, you'll know that that is rhenium, Re. So there you go. That's an intro to stoichiometry and counting by weighing. I think you're going to like the demos we do over the next couple of days because they really help to highlight this.